Hey guys, so here's another classic example of conservation of angular momentum. And here we have this weird setup where you have an object, a little block, that spins on a horizontal table. So imagine you got a table and you have an object spinning on top of it, but there's a tiny little hole through the table, and the object spins because it's being pulled by a string that is pulled through that hole. So you might be wondering what's up with that setup, right? The reason we have these weird setups is because we need a way to change the length of the cable, which will in turn change how quickly the block on top spins. The block on the bottom is just being used to hold, to give this cable some tension. So this guy here is being pulled by mg, and therefore there's a tension here, and this tension is what provides the centripetal force for this guy here to spin. Okay, so that's the standard setup, and basically what's going to happen in these problems is the length of the cable will get reduced, which means the r, the distance of rotation around the central axis, will get reduced, which means the omega will go up. The object will spin faster and faster. So let's check this out. It says here we have a small object, the red one over here, has a mass of 2 kilograms. It is in a smooth table, no friction, attached to a light string, no mass on the string, like always, that runs through a hole in the table. The other end of the string attaches to a hanging weight, this guy over here, M2. So M1 is 2, and M2 doesn't get mentioned yet. It says when the small object is given some speed, so you give this guy some velocity here, v, whatever, and it's going to start, right? It's not, the v, by the way, it's tangential to the circle. I drew it this way. It doesn't mean that it's flying off the table. It's just going this way on the table, right? So it has some velocity. Maybe I should draw it sort of like this. It doesn't look like it's going away. All right, so when it's given some speed, it spins around a circular path around the hole with a tension from the hanging weight provide a centripetal force. I explained that this mass here pulls down, which the block pulls on the rope, providing the tension, and this tension is what keeps you spinning because it provides the force that keeps you around a circle. It says, suppose that the object spins at 120 RPM when the radial distance, when it is a radial distance of 10 centimeters from the hole. So when this distance L or R is 0.10 or 0.1, it has an RPM of 120. So this is how the problem starts. Therefore, I'm going to call this my R initial and my RPM initial. Okay. So the first question is, how fast in RPM would it spin if the radial distance was reduced to 6? In other words, if our final is instead of 10, it is 6, so 0.06, because it's got to be in meters, what would be my RPM final? Okay, so that's part A. So let's do this real quick. Conservation of angular momentum. L initial equals L final. I'm going to expand this to be I omega equals I omega. Initial, final, final. This object is a small object, which means we're going to treat it as a point mass. So instead of I, we're going to expand I into mr squared. And notice that I have RPMs, so I don't want omegas, I want RPMs. Remember that omega is 2 pi f, or 2 pi RPM over 60. So I'm going to rewrite omega, expand omega as 2 pi RPM initial over 60. This is mass initial, though the masses don't really change, and the radius initial, or the distance initial. On the other side, I have the same thing, but it's going to be m final r final squared, and then 2 pi RPM final, which is my target variable, by the way, divided by 60. When I write this, notice that I can cancel some stuff. First, the mass doesn't change, so this mass cancels with this mass. The 2 pi cancels with 2 pi. 60 cancels with 60. So we're left with Ri squared, RPM initial, equals R final squared, RPM final. And this is what we're looking for. So I can solve for RPM final by moving everything, by moving this guy to the other side. So it's going to be RPM final is Ri squared, Rf squared, RPM initial. So notice how the RPM final is the initial RPM times a ratio of the squares of these distances here, right? So the initial one was 10, so 0.1 squared. The final one is 0.06 squared. And the RPM initial was 120. So if you do all of this, you multiply it, you get 2, I got it here somewhere, it's 333. So remember I mentioned how it was going to be faster, and indeed it is faster. The final RPM is going to be 33. So that's part A. Let's keep going. For part B, it says up here, at this new RPM, what linear speed would the object have? So I'm basically asking, remember when you spin around a circle like this, you have an omega, and you also have a corresponding and equivalent tangential speed v tan. And remember that v tan is connected to an omega by v tan equals r omega. So we're saying at this new RPM, what would be your linear tangential speed? So what would v tan be? Let me just do this. Okay, so all I got to do is multiply r times omega. Now I want the new or final v tan, so I'm going to use the new or final r and the new or final omega. So the new r is 0.06. I don't have omega. I have the new RPM, but I can plug it in here. So it's going to be 2 pi RPM final divided by 60. So this is 0.06 times 2 pi times RPM final is 333, and this whole thing divided by 60. And if you multiply all of this, I got it here, you get 2.1 meters per second. 2.1 meters per second. That's part B. It's another thing you might be asked since there's a relationship between those numbers. And then for part C, we're being asked what mass M2 does the hanging object need to have? So in other words, what is M2 to maintain the small object spinning, at the RPM found in parts B. Now, this is actually RPM found in parts A, right? The RPM found in part A. Okay? Cool. So what M2 do we need in order to give it that speed? And the idea here is that this mass, M2, this is M2G, matters because it is at equilibrium. So this tension here equals M2G, and this tension here is the centripetal force that keeps this spinning. So this, if you change this, you change the amount of centripetal force. Okay? So we're gonna, this is really a centripetal force problem. So now I'm gonna write that the sum of all forces centripetal equals MA centripetal, and then I can rewrite this. The centripetal force here is, the tension, which comes from M2G. So I can actually rewrite this as M2G, M, and then acceleration centripetal, I don't have it, but I can rewrite it as V squared over R. Remember, in a lot of these problems, of centripetal force, you rewrite F equals ma into F equals mv squared over r. Okay, so you should remember doing this stuff. I want to point out that this mass here is, this is the acceleration of the block, so this is actually going to be m1. So what we're doing here is we're trying to figure out what is m2 so that m1 can spin at this RPM, which, by the way, this RPM produces this speed. So the idea is you're going to plug 2.1 here. All right? So to solve for this, I have m2 equals m1 v final squared, because we want to know how much mass we need to support it with the new rotation, and that is divided by gr. Okay? So m1 is 2. The velocity we found is 2.1 squared. G is 9.8. And obviously, if we're talking about VR, V final, we're talking about R final as well. R final is 6, so it's 0.06. Okay? and you multiply this whole thing and you get 15 kilograms. So the idea is that for you to be able to spin at 133 RPM, which means you have a linear velocity of 2.1 at that distance from the middle, M2 has to be 15. If you want to spin even faster, meaning this V here would grow, you would need your mass to be the hanging weight at the bottom to have a greater mass so you can have more tension so that this thing can spin faster. All right, so that's the idea. I like this example because it touches up on a bunch of different parts of this question that you can get. The most common one is part A, but you might see something where you start talking about the hanging weight and what happens with the hanging weight as well. Okay, so that's it for this one. Please let me know if you have any questions, and let's keep going.